Hey everyone, you're watching the Space Channel. Black holes are rightly considered among the most mysterious objects in the universe, and they're surrounded by tons of myths. That's why we decided to make an entire video series debunking them. In the previous episode, linked in the description, we covered the first four. Today, we're taking on four more popular black hole myths. Let's dive in. Myth 5. A black hole will definitely tear apart a person falling into it. This myth has a factual basis, because a body approaching a black hole is acted on by tidal forces caused by the non-uniformity of the black hole's gravity. The point is that the closer we are to the source of gravity, the stronger it pulls us in, and this force increases by literally every nanometer of approach. Because of this, the part of the body that is closer to the black hole is attracted more strongly than the part that is farther from it. In fact, every atom of the body is attracted to the black hole with a different force. And it is precisely this difference in force acting on neighboring particles in the body that is called the tidal force. That name was chosen because this very force causes tides and ebbs in the ocean. Under the action of tidal forces, a body is stretched in the direction of the black hole, or as Stephen Hawking called it, spaghettified, and at a certain point, when the body turns out to be close enough to the hole, it will be torn into atoms. But when exactly this will happen depends on the size of the black hole. Paradoxically enough, the larger the black hole, the more uniform its gravity is, and the weaker the tidal forces will be. As a result, for giant black holes with masses of millions and billions of solar masses, the boundary at which a body will be torn apart lies beneath the event horizon. That is, a body can approach the black hole and cross the event horizon unharmed, whereas small black holes will indeed tear anything apart already on approach. Myth 6 states that black holes can appear only as a result of a star's explosion and that they are only enormous. This myth goes way back. At the dawn of general relativity, when the equations describing black holes had just been obtained, the question arose of how they could form, and the first possible scenario turned out to be the collapse of a massive star into a black hole. It was precisely this image that entered popular culture. However, over time, other mechanisms for black hole formation were discovered, and it turned out that they can have a wide range of sizes. Thus, micro-black holes can form when microparticles collide at enormous speeds, or due to random oscillations of space-time curvature, called fluctuations, and their sizes and masses can be comparable to those of atoms. Another class of black holes is primordial black holes. They formed soon after the Big Bang due to fluctuations in space-time curvature. Their masses should be commensurate with those of planets, and they are about the size of a basketball. Potentially, some of these black holes could have evolved into large ones through the constant accretion of matter. But this has not been confirmed so far. There is also a theory of black hole formation via the so-called direct collapse, skipping the stellar stage. This can occur in very massive gas and dust clouds when the flux of radiation and matter from a newly formed star is insufficient to stop the infall of matter onto it, and the cloud rapidly collapses into a black hole. This mechanism has not yet been thoroughly studied or confirmed, but it is the best explanation for the appearance of supermassive black holes in the cores of galaxies that were the first to form after the Big Bang. At the moment, the existence of stellar mass black holes and supermassive black holes has been reliably confirmed. As for other types, there is no observational confirmation yet. According to the seventh myth, the image of the black hole presented in April 2019 is, in the literal sense, a photograph. For those who didn't know, in April 2019, the world was presented with the first image of a black hole's shadow, including the event horizon and the accretion disk. It was the black hole in the galaxy M87, located at a distance of about 54 million light-years. In scientific publications and serious popular science outlets, the method for obtaining this image was specified, but many media outlets chose to keep quiet about it or describe it inaccurately. When a regular photo is taken, The camera collects data in the visible spectrum about colors and the intensity of the glow, then converts it into an image. With the black hole image, everything became much more complicated. The data were collected outside the visible spectrum by different telescopes at different times. Then all this data was processed, and based on it, a simulation of the black hole was created. Based on this simulation, an image was generated showing what the black hole would look like in the optical spectrum. This image turned out much sharper than shown, and it was additionally blurred to match the telescope's resolution. Therefore, the displayed image is not a photo, but a visualization of the obtained data. Well, and lastly for today, myth number 8 claims that black holes do not shrink, but only grow. This myth is still pervasive, even though the concept of Hawking radiation is actively entering popular culture. The point is that in a vacuum, pairs of virtual particles are constantly being born and annihilated. Under normal conditions, nothing can prevent their annihilation, and we cannot detect them. But near the event horizon of a black hole, the situation changes. The particles in each pair are born at some minimal distance from each other, so the enormous tidal forces of the black hole can separate the particles and keep them from annihilating. Then one particle falls into the black hole, and the other flies away. In this case, the black hole effectively performs the work of separating the particles and turning them from virtual to real, thereby expending its gravitational energy. Since mass and energy are related, when a black hole's energy decreases, its mass decreases as well. It follows that the black hole shrinks in size. This process is called black hole evaporation, and sooner or later, a black hole that is not accreting matter will completely evaporate. However, this will take a very long time. Even for a relatively small black hole, it will take hundreds of billions of years. And the larger the black hole, the more slowly it evaporates, because it has weaker tidal forces. Another mechanism for reducing black hole mass is gravitational wave emission. This can occur in a binary system containing a black hole. A black hole also expends energy in the emission of these waves, thereby reducing its mass. Moreover, right before the merger, in the last seconds, a simply enormous amount of energy is radiated, which in observed cases was comparable to 10 to 20% of the mass of the merging black holes. If you enjoyed this video, give it a like and subscribe to our channel, and in one of the following videos, we'll talk about a new batch of myths about black holes. See you next time.